Material Science, led by Kim Verbeken. And together with Kim, we are developing strategies against corrosion and hydrogen embrittlement and to increase the lifespan of metals and constructions. Today's talk will focus on the corrosion topic, which fits nicely in the capture pipeline on water fit for use. Increasing the lifespan of material and constructions can lead to sustainable use of resources and energy, while a reduction of the CO2 footprint can be obtained. If we want to meet the European target of zero CO2 emissions by 2050, we have to make appropriate material environment choices to optimize this lifespan and to, in the end, obtain ecological and economical gain. What can happen? During lifetime, a material can come in contact with a specific environment. With that environment, the material will interact, and this can lead to degradation of materials. This is known, for instance, as corrosion. And to give you an idea, the cost of corrosion is about $500 billion per year only in the US. The performance of materials will decrease with time because it will degrade with time due to the interaction with the environment, and therefore maintenance and replacement is needed. However, the moment when you do this is quite crucial. If you do it too soon, you have useless costs, and if you do it too late, you have possible failure. In the end, you have three parameters that interplay. You have a specific environment, a material, and then a stress to which the material is experiencing. And these three parameters can lead to environmental assisted cracking, the center of these three parameters. First, I will talk about corrosion of turbine blades in steam water cycles. Water is very important in industry for a lot of processes, such as the generation of electricity, for instance, shown in this video. 80% of electricity is generated, produced through the use of steam turbines via steam water cycles. Due to the ongoing shift towards alternative water sources and the use of new water treatments, different types and concentrations of contaminants, such as, for instance, organic acids, chlorides and carbon dioxide are present in the water, and this can lead to large problems. For instance, due to steam water partitioning of organic acids, the first condensate is typically acidified, and this can be quite tricky. This acidified first condensate can cause significant corrosion damage to the steam turbine, which might lead to unexpected stop of the power plant and of course then produce important losses. As explained, corrosion can be defined as the undesired degradation of a material caused by an electrochemical interaction between a material and its environment. For instance, in this acidic aqueous environment, reduction of oxygen and hydrogen can take place, leading to hydrogen embrittlement, the two first reactions, while metal atoms can go into solution by oxidation, the third reaction given here. And as such, the metal can slowly dissolve in the water. This is called corrosion. In the improved project funded by Interreg, we investigated this acidic stress corrosion cracking. You can see at the left-hand side, you can see such a crack there. This is, of course, undesired. There are a few things you can do while focusing on these three parameters. For instance, you can play with the material, so you can change the microstructure. You can include precipitates into the microstructure to trap hydrogen so that no embrittlement takes place. So this is on a material level, but you can also change the environment. For instance, you can add an inhibitor like fill-forming amines to the environment to protect your metal from corrosion. A third option is elimination of organics, of course, because these organics lead to organic acids and are responsible for acidic stress corrosion cracking. At the right-hand side, you can see the corrosion rate of this turbine steel in micrometer per year. And as you can see, if the pH is dropping, so in more acidified solutions, the corrosion rate increases. In this study, we tried to differentiate different types of acids. And as you can see, formic acid is the worst one. So the corrosion rate was the highest for formic acid. While, for instance, nonanoic acid behaved as quite inhibiting to corrosion. So this is beneficial to add. This is purely electrochemically and material related, but what's also important is the stress. So that's why we also do in situ constant extension rate testing. Quite a long name, but basically we do a tensile test. So we pull on the material and we do it in air as a reference, but we also build a chamber surrounding that material. And in that chamber we have full control, and we can control pH, temperature, we can have some gases present there as we want. And then we can see the influence of that environment to the mechanical integrity of a metal. In blue you can see the stress strain curve in air showing normal behavior. But when you then have this chamber with a specific environment, with this acetic acid present, you can see a drop in strength and a drop in ductility. If you increase the concentration of acetic acid, as you can see here going from 0.01 to 1 molar, you can see that you lose more ductility. Now the question is, of course, how can we understand this? What is the mechanism? What is responsible for this ductility drop? If we combine these results with electrochemistry, we can plot the corrosion potential versus the pH. And what is striking here, that at pH below 4, you see that these points drop well below the reduction line of hydrogen. So for these low pH data, we have both oxidation of steel, so corrosion, but also hydrogen embrittlement, because hydrogen protons will be reduced and atomic hydrogen can be taken by the metal. So in this case, both mechanisms play a role, and not the dissolution of a metal, but also hydrogen embrittlement. And to prove this, we took this data point at 3.5 pH, more or less, and we took a look to the surface. And if you take a look to that surface, we can see hydrogen-assisted cracks, indicated by the red arrows. To prove that this mechanism or this change happened, we analytically polarized that pH level, that sample, towards just corrosion potential above the reduction line of hydrogen, so the green dot. And if you take a look to the surface then of the green dot, we see no more cracks. So this is a proof that when we go below this reduction line of hydrogen, we also have hydrogen embrittlement taking place next to anodic dissolution. This was the story on the Improve project. We are now involved into the Sakura project as well, which is an ongoing project. And here the idea is to evaluate sensors to monitor environmental parameters like pH, temperature, dissolved oxygen, chloride content, salinity, and so forth. So here we focus on corrosion in wastewater treatment sites and marine environments. And the goal is to have statistical methods to mine data for corrosion risk estimate. So again, three different aspects will be taken into account. Here we will tackle, or we will use it as a solution, not acidic acid, but we will use seawater. In the lab, we will use artificial seawater to fully control the conditions, but we will also use Austin seawater to also include, for instance, the role of the microbial activity. Three different material grades are also included, and we will start with the electrochemical aspect. As explained before, the corrosion rate will be determined. Corrosion potentials and also pitting potentials are quite important, but these are all quite static. What do I mean with static is that there is no water flowing over the material. If you have flow, if you have dynamic conditions, and if liquid is flowing over the metal, you have a different situation and corrosion is worse. So that's why it's important to also include studies on rotating cylinder electrode tests to study flow accelerated corrosion. In this way, we can control also the flow of a certain liquid over the surface of a metal. So this is the electrochemical aspect. Again, next we go to the mechanical aspect, and I explained you the set testing, so the tensile testing, but here we will use also a standardized 4-point constant extension testing. Here we will put materials under stress in a container. You can see the containers on the right, and in these containers we have full control of the environment. After 1 month of exposure, we will take the samples and we will go to the SEM to see the scanning electron microscope to see if we have some cracks or some pits formed or if some damage happened. And in this way we'll try to understand the mechanism and to improve it that corrosion no longer takes place. So the final important aspect is in the microstructure, because we want to understand what happens on a microstructural material level. And these are then these pictures, for instance. This was a study on sour corrosion. So in the case we form iron sulfides. So in this case, you can see in the colors at the bottom, you have the steel, and then on top you have two corrosion products. It's not just one, it's mainly iron sulfide, but you see that there is different presence of chromium and molybdenum. And indeed, the main composition of both layers, of both corrosion layers, was machina white. However, they contained different amounts of alloying elements, moly and chromium. The upper layer was created by a precipitation from the solution and was enriched with molybdenum, while the inner layer was formed via uniform corrosion and was enriched with both molybdenum and chromium. This is because molybdenum can undergo deposition reaction, while for instance chromium will not undergo any deposition but will remain in solution as chromium 2+. This formation of the corrosion product also has an influence on the hydrogen uptake. As you can see on the right hand side, you see an increase in hydrogen content in the beginning when there is no corrosion product present. But once you have this corrosion product, you see a decrease in the content of hydrogen. This is because a lot of hydrogen is already released outside the iron sulfide layer and will be lost to the environment as H2, so molecular hydrogen. By combining the environment, the stresses, and the material, we will be in the center of these three important parameters, and we will be able to evaluate environmental assisted cracking. And thank you for your attention. I'm looking forward to your questions.